the cloud. Okay, welcome. Here we are again, starting the 2019 Planetarians web seminar series. And to start off this month, we have Doug Duncan from the University of Colorado to talk to us about, it's not what's showing up on your screen there. The title, the official title that we have been publicizing, I'm going to write in the chat. Let's see. And by the way, this is a little reminder to people that there is a chat. And if you have questions, you can keep track of them in the chat if you like. I'm typing in the chat right now. The actual title that we publicize is Active Learning in the Planetarium for 100 students at a time.
Yes,
and,
sir.
Doug Duncan has been at the Fiske Planetarium for quite a while now, and I've put his email address in the chat too for those of you who want to contact him with more questions after this seminar. But I'm going to go ahead and turn it over to Doug now.
Well, thanks very much, Alan. We did a test, and I think I'm coming through loud and clear for most people. I love planetariums and talking about them. I think it's fun and perhaps relevant. As I was mentioning a few minutes ago, I started in 1968 as a student volunteer at the Griffith Observatory. I was in high school in Southern California, and actually I was hired to sell tickets and answer the phone. But I waited for my chance to be a planetarium presenter because they made $25 an hour in 1968. And sure enough, one of the lecturers got sick, couldn't lecture anymore. They were looking for somebody. I raised my hand and said, try me. And I was very lucky. I was the youngest person ever hired at Griffith to give shows at the age of 19. And so I did that all the way through college till I went off to graduate school. So fond spot in my heart for planetariums, and I'm glad to be back at a university that has a big one, although big planetariums are their own challenges. So let me tell you a little bit of the background here. We have a lot of money at the University of Colorado to do research on college students' learning and non-learning of science. And that research involves interviewing lots of students, making videotapes, having them talk aloud about their understanding of different things. And we have a beautiful planetarium. It was given by a donor to everyone's surprise back in the 1970s. And one reason I came here was to modernize it. And so about 5 years ago, we turned it into a beautiful 8K by 8K video planetarium, and also a thing called Megastar, which is kind of like the thing that made Zeiss very sad because it's an optomechanical projector, but it does 20 million stars. You can use binoculars and you can scan the Milky Way, and it's just a beautiful setup. But we have this tradition here now of measuring how much students learn. So a pretty good question for planetarians is, what kind of program results in the most student learning? Now, I'm very aware that I think it's very important, that planetariums do a lot of things. We entertain people, we inspire people, and we teach people. This talk today is just about the teaching and how much they learn. So if your goal is to have students visit your planetarium and learn pretty well, what kind of program should you present? You know, is it the storytelling that enhances their learning? Is it the quality of the visuals, how professional the production is? What is it that's important specifically for student learning? Well, I'm a little bit blacked out in my screen here, but it says leading author, printer, political theorist, politician, postmaster, scientist, inventor, humorist, and statesman and diplomat, Ben Franklin is the one who said this. So even a couple of centuries ago, good old Ben was onto the fact that involvement and students doing stuff, not just hearing stuff from us, is a good thing. So we have all this data taken in many, many, many college classes, not just here, but across the country. And maybe, probably some of you have seen this data, maybe not all of you. If you're a teacher and your teaching causes you to explain stuff to students, so you do the talking, but you're a good explainer, you prepare well, and you explain as clearly as you can, what fraction of your students do you think master what you explain? And it's important that I explain what I mean by master. By mastery, I'd say that means you understand something well enough to explain it to somebody else. So you explain the cause of the seasons to all your students. What percentage of them, if your explanation is good and clear, and maybe you show a picture or point something out, what fraction of them could then explain it to somebody else? What do you think?
B.
Well, here's the data. 25%.
Oh.
This is based on a survey of over 6,000 students in 52 classes. And the x-axis of this plot is the fraction of everything taught in the semester that the students mastered. Obviously, it doesn't say they scored 25% on their exams, but you can infer from those two pieces of information that exams don't probe very deeply, especially most multiple choice exams. So just presenting something clearly to the students gets you to about 25%, which was not very encouraging to us, shall we say. And this is what we learned 10 or 12 or 15 years ago. So that's when we really got the impetus to try some different things. So just to repeat and enlarge on what I said, how do I really know this? This is our methodology, and it's been going on for, in my case, 16 years. So we really do. We pay students $10, and they come in, and we have them try and learn something, and we videotape them. And we do this over and over and over again. And if you have seen a few of the standardized instruments, such as the Astronomy Concept Inventory or the Light Concept Inventory, this is how those are constructed. You interview maybe 100 students, and you find out what their common wrong ideas are. And then if you want, you don't have to do this, but you can make up something like the Light and Spectra Concept Inventory, which then has maybe 20 multiple choice questions where all of the wrong choices are things that are based on the student interviews. So a fascinating thing to me is that this research shows about half of the things, roughly, that students get wrong, they get wrong year after year after year, semester after semester. So they're always going to get the seasons wrong. They're always going to get the phases of the moon wrong and certain other things. So knowing that is good armament, so to speak, I think, for people who teach, that you know what's going to be tough for your students. So you know a little more what to concentrate on. And these are all questions about concepts, not about numbers. Yeah, isn't that fascinating? If Aristotle got it wrong, by the way, the students get it wrong too. Okay, so one of the problems is that almost all people who teach astronomy overestimate the depth of their students' learning. And this is kind of a classic study. I'll show you the person who did it in just a minute. And on all these different subjects that have to do with astronomy, he asked the people who teach, what do you think, what percentage of knowledge do you think your students will have at the start of the semester and at the end? And so the uncolored bars, the squares, which typically started around 30%, most of the people who taught said my students would score 30% on these topics on an exam at the start of the semester, but after I'm done teaching them, they'd be up where the black boxes are, more like 70 or 80%. And on the basis of individual student interviews, the actual performance is what's colored in kind of fluorescent green. So the actual learning of students is a lot less than most people who are teaching them think they're learning. By the way, the person who did this is Phil Sadler. Some of you know him, and you all should know him. He invented the inflatable planetarium. The original one was called Star Lab. But more germane maybe to us right now is he did a fantastic study called A Private Universe. And I don't know if there's any easy way, Alan, for me to get feedback, but I'll just say, if you're watching today and you have not seen A Private Universe, it is absolutely worth your while to go watch that video. It's like 15 minutes long. Most of it is on YouTube. Just search for A Private Universe. It's filmed at the Harvard graduation, and it's concentrating on how hard it is for students to learn something when they come into our classes with a misconception, like about the seasons or the phase of the moon or something like that.
Doug, if you want to get feedback, there's a couple of ways we can have people unmute and say things, or there is a chat window. You can open your chat and see what people say.
Oh, there's the chat. Okay.
Because people put in some of their answers to your first question there.
Yeah.
A few people did.
Oh, okay. Well, why don't I ask everybody, please, have you seen the video A Private Universe? Oh, you guys are good. Okay. Every answer I got is yes. Well, good old Phil Sadler isn't lying. You know, it's not enough to put information out to the students. Although the students think, a majority of students think that learning is mostly about information, and they can kind of sit there in the planetarium or in the classroom and you're going to fill their head with knowledge. But of course, it does not really work that way. So you could say in the planetarium, we don't just tell them things like in the classroom, we show them stuff, right? And sometimes with a video planetarium, we show them dramatically. Isn't that better? Well, not much, okay? Again, a lot of times planetarium's used in a passive way, kind of like demos. Everybody loves physics and chemistry demos, but research shows it only bumps up their learning by maybe 5% if they just watch. If you can get them to participate somehow, then that works better. So I think the common thread is learning takes place in the mind of the students. And in order to learn something new, they actually have to pass through some period of time where they're not sure. Scientists are comfortable with that, right? I mean, we study a lot of things. We may go years not being sure what's out there at MU69 or whatever. We're comfortable with that. Our students are not, but maybe it's worth reminding them that when you learn something new, it's okay to be confused for a while. They don't always think that. Okay, so how do you get students to be able to learn something, see something in the planetarium, but maybe they don't instantly understand what it means, so they need to be confused for a little bit, and then maybe they figure it out and make it their own? Well, if you think about it, that kind of learning takes some time. And so it might occur to you that the more polished and professional a planetarium presentation is, actually the less time it leaves for the students to stop and be puzzled and then move on and learn something new. And it turns out that there was a fascinating PhD student by a man named Derek Muller, and you're seeing him in front of you now. And although his PhD was about making science teaching videos, I don't see why it doesn't exactly apply to planetarium presentations too. So I think you'll really enjoy, it's only about a 5-minute video of what he learned in his PhD thesis about what makes a good presentation. Listen to what Derek has to say. And by the way, he now has his own YouTube channel. And if you root around, I think you can find this TEDx talk. Oh, come back, Derek.
Question, how do you make a film that effectively teaches someone something about science? That was the topic of my PhD. So I'd like to tell you what I found out. I went to the University of Sydney and I took all the first-year physics students and I tried to teach them about the basic laws of motion, Newton's first and second laws. So I sent them away to their homes and I asked them to go online and sit a 26-question multiple choice test. Here's a sample question, just so you get a feel for what I was asking them. Imagine a basketball player shooting from the free throw line. After he releases the ball, the forces on the ball are A, upwards and constant, B, upwards and decreasing, C, downwards and constant, D, downwards and decreasing, or E, tangent to the path of the ball. I want you to take a minute and think about what you would answer, and think about what you think other people might answer, okay? So then we would get the students to rate their confidence in their answers. How confident are you that this is correct? I should mention that is not the exact Likert scale that I gave them, but it's, get the idea across. Okay. And then I would randomly assign these students to watch one of several videos about Newton's first and second laws. They lasted about 8 to 10 minutes. So in a standard exposition video, I would say something like this to them. Well, we would state Newton's laws, and then we would apply it to a real world example, like a juggler. I can't juggle, so I've got one ball. Anyway, so we would say something like, while the ball is in the air, there's only one force acting on it throughout its flight. It's the force of gravity, it's constant, and it's downwards. We'd actually animate a little arrow on the ball as it goes up and down in slow motion. Okay, so obviously the answer was C, whereas most people usually pick B for that question. Okay, so after watching this video, the students would sit the exact same 26-question test. I wanted to see, have they changed their minds about any of those questions? And I also interviewed a couple students to see what did they think about the video. Did they like it? Did they think that they learned something from it? And here's what they told me. Well, they said, Derek, that was a great video. It was clear. These are the most common things they said. It was clear, it was concise, it was easy to understand. Good. And then I looked at their confidence scores. How did that change on average? Well, on average, it improved by about a point. Okay, everything's looking good. But how much did they learn? Well, on the pre-test, they scored 6 out of 26. And I can tell you there were basically direct answers to at least 14 of those questions. But how much did they pick up? The average on the post-test was 6.3. What happened? They thought they learned, but their scores didn't change. Well, one of the students told me, in the video it said, the ball is slowly decreasing in force. They thought there was some upward force in the ball, and they thought that was presented to them. They couldn't even correctly remember what was presented 5 minutes earlier. And I had sat in the room with them, and they watched the video. The thing is, in science, students don't know nothing about what we're trying to teach them. They actually know lots of things through their interaction with the world. It just turns out that these things are wrong, scientifically speaking. So when you present something, the student thinks they already know it, and they don't really pay utmost attention. They don't realize that what's being presented differs from their prior knowledge, and they just get more confident in those things that they were thinking beforehand. So actually, a clear expository summary is worse than no instruction at all. I mean that very seriously. So how do you get students to engage? Well, I tried a different approach. I put 2 people in a video, and I got one to voice the common misconceptions. And then the tutor would kind of indicate, okay, that's not quite right, and they would work it out through a social dialogue. But I mean, we would even animate the misconception on the ball without telling anyone it was a misconception. They had to work that out through the social interaction. Okay, so this was the very same setting that the other students watched the exposition video. What did the dialogue students say? Well, no one told me that it was clear. No one told me it was concise. No one said it was easy to understand. In fact, most of the time, they told me It was confusing. Maybe this backfired. How'd they go on the post-test? Well, their scores nearly doubled to 11 out of 26. Okay, it's not 26 out of 26, but it's a start. And what was the difference? Well, after the video, I asked students to rate their mental effort. How much mental effort did you expend while watching that video? And the students who watched the dialogue invested significantly more mental effort in engaging with that presentation than students who saw only an expository summary. So to me, there's a really important message there. Depending on how you present, you can change how your audience watches and thereby how much they learn.
So I think there's an interesting challenge there for us in the planetarium. You know, for 30 years, I work and work to make my planetarium presentations as smooth and professional as possible. But now I've gone to really thinking where to break the presentation, where to stop talking, where to toss it into the laps of the students, and how to get them to really expend the mental effort that they need to learn. And by the way, I do warn them about this. I show them that cartoon and I say, you know, we're going to go in the planetarium and we're going to try and visualize some stuff that's hard to visualize. And I will show you some things, but really the learning has to happen in your brain. And when you point things out to each other, we're going to break you into little teams of 3. That's when you're really going to learn. So setting it up kind of metacognitively like this is a good thing. It's tough for me to admit this to myself because I love my honed planetarium explanations. But like I said, we're really pushing to get the students to think more. So here's a couple of examples. By the way, when we have a big group, if I want to know what they're thinking, we have them bring their clickers. Our university has 20,000 clickers in circulation. It's kind of like pens and pencils. So the students are used to are monitoring their feedback. So when we talk about summer and winter and the sun's motion, I used to be very careful about pointing out, you know, here's what it looks like, here's where it rises. Now we start out by letting them figure it out. They've supposedly read the chapter in the book. So the planetarium owns about a dozen giant arrows in A, B, C, D, E. And so we do things like saying to the class, okay, it's summer here in Boulder, Colorado. Where do you think the sun's going to rise and set? And of course, with 100 students, you can't get everybody up and volunteering, but I'll sometimes get maybe 2 at each arrow and 5 arrows for sunrise and 5 arrows for sunset. So we got 20 people up there actively, but then the others have to commit themselves and vote. Do they think the sun's going to rise at A or B or C? Who do they think is more accurate? So that's how we treat something fairly straightforward like the seasons and the different paths of the sun. This is their book that they use. Right, and so that's how we try and teach that now. But we've moved to something much more comprehensive and more fun, and it's what we call Survivor. We simply tell the students we're going to drop them at an unknown location in the Northern Hemisphere, and we've taught them that their fist at arm's length is 10 degrees and their finger is 1 degree. And they can ask the planetarium operator to show them anything they want. Now, before they leave Boulder, we let them observe. So they can watch sunset or sunrise or nighttime in Boulder. We don't tell them what time of the year it is. Then we instantly transport them to someplace else on the earth, but it is the same day of the year. They don't know what time of the year that is. And we want them to determine 2 things. One, where are they approximately on the Earth? And two, about what time of the year is it? And they have to completely come up with a method. And the way we do this logistically is everybody gets a whiteboard. Well, not everybody. The students break into groups of 3. Whoever happens to be sitting on your left and right, you're a team. And you get a whiteboard, and we give them, I don't know, maybe 10 to 15 minutes to make a plan. So we don't really show anything in the planetarium until they ask for it, until they're ready. And then when they're ready, we show them things here at home, here in Boulder. So they usually want to see sunset and sunrise, and they look and see where that happens and when it happens. They have their watches set to Boulder time. So for instance, they can say to the planetarium operator, please make the sun set. And if they don't have their watch, I forget what I just said. They ask for sunset, and then they ask the planetarium operator, what time is this? So maybe the sun is set at 6 p.m. in Boulder. When they're all done looking at the sky at home, that's when we transport them to a new place. And they can, again, ask to watch for sunset and sunrise. And they're going to find that it happens at a very different hour, even though it's the same time of the year. And then they look at night, and they're pretty good about looking for Polaris to try and find something about their latitude. And just like in real life, longitude east-west is usually harder. Most of them have heard of time zones, but they've never stopped to think what they are. But we do let them play around with a little globe and talk to each other and start to think about, why does the sky look different? And we probably spend a good 30 minutes, maybe even 40. And then they're supposed to figure out where on the Earth they were taken to and about what time of the year this is all happening. So they learn somewhat more doing this. The orange dots are when we would bring classes to the planetarium and show and tell in the usual way, and then give them an exam about where does the sun rise and set in summer. And their average success was about 45 or a little under 50%. Now, to be fair, in this survivor activity, the emphasis is on where you are, not very much emphasis on where does the sun rise and set in summer, but it is something they see. So the students in the survivor activity are certainly doing better, though not as well as I'd like them to do. So when I run it this year, I'm going to put a little more emphasis in noticing maybe the difference between summer and winter. However, there's another thing that's important to us, since these are non-majors. What do they think about it? And the answer is they really like it a lot more than the old-fashioned show and tell. Here's a typical quote. And it's, of course, more like science, because they have to come up with something creative, and then they have to test it with their observations. So we're pretty happy about this aspect of it, that they feel like they're doing something a little bit special. We have labs which only have 25 students in each lab, and we also bring labs to the planetarium to do survivor. So we do it in a group of 120, but we also do it in multiple groups of 25. It's easier with 25, but you can do it with a full class. Interestingly enough, the US Navy ROTC has started coming to our planetarium 2 years ago. And apparently the Navy has realized that you can't always depend on GPS in, say, a wartime situation. So they are teaching the cadets old-fashioned celestial navigation more quantitatively than our intro students do it, but of course it's the same thing. With our nice megastar, the Navy says it's just as good teaching their students indoors at the planetarium as it is on some actual ship, and we're closer to campus. We're trying to find more activities where the students take the initiative and predict what's going to happen. We now have CU Stonehenge. It's a pretty cheap Stonehenge. We put a post up outside the planetarium, and all of the 120 students have to get together and figure out where the shadow of that post is going to fall on a given date. And each group of students gets a stake, and they put it in, and then at sunset on the chosen date, they're invited to come, even though it's outside of class hours, and see who the winners are going to be. So I wish I had even more activities that get students leading and figuring this stuff out, but that's what we've done so far, and it seems very rewarding. I guess I will close. I'll summarize, but then I'll make one editorial comment. Students need time to think and be confused a little bit in order to learn something new. So however you make your presentation in a planetarium, don't make it smooth and nonstop. Give them chances to figure stuff out for themselves. Encourage them and tell them explicitly it's more work, but you're going to remember more. So it's worth their while. And it's fun and it's creative. And so my editorial, oh, and you know what? You've seen this before too. Predict, observe, explain. It's really kind of bringing that methodology into our planetariums. The reason I think that this is important is in 2001, almost 20 years ago, I was at the University of Chicago teaching. And I also volunteered to teach the non-majors class. And I was lecturing in those days. I was just starting to do some peer instruction. Mazur's book on peer instruction hadn't been published yet, but I was experimenting in that way. But I stopped one day and I looked at all my 70 students and I thought, wow, you're all University of Chicago students. You're pretty much straight A students. And none of you are science majors. I wonder why. So I stopped and I asked my students, did any of you ever think of majoring in astronomy or some other science? Would you please take out a piece of paper and just write down, did you ever consider a science major? And I collected 70 pieces of paper. And then I started going through them and reading them. And about number 10 or 15, I started hitting my forehead. Because a common theme was a student writing that began like this. It began, no, comma, I'm a creative person. And therefore my major is, English or whatever it was. But it was clear from what the students wrote, they didn't think science was very creative. They got A's in it, but they were never put in the position where they were the creative one, or very rarely. So I think the fact that students can be more original and have some creativity, even the non-majors, is pretty important to their understanding of what motivates us. I suddenly realized that I was behaving so prim and properly in front of my class at Chicago. And they never go to meetings. They never see, 3 astronomers arguing over what MU69 means or anything else. So they kind of miss the fun and they miss the creativity. They think everything is an answer in a book. So if you can think of some things, they get to be creative. It's great. Even I got to say this on this example of predicting where the sun is going to set over our beautiful Rocky Mountains on whatever, March 15th. Their book comes with a planetarium program. And some of them even have something on their phone. And so they think, oh, this is going to be easy. And they set the planetarium program to the date and they see, oh, it's a little bit off from west. And they go outside and then they have this kind of amazed look and they all look at each other and they go, where's west? And somebody says, well, it's where the Rocky Mountains are. And then somebody else says, gee, is that accurate enough? And then somebody says, hey, wait a minute, there's a street in Boulder called Baseline. And I think it runs exactly east-west on the 40-degree line. And they go, yeah, but that's way across campus. How can that be useful to us here? And then some student marches with says, can I have a protractor? And we give them a big protractor. And they march to Baseline and they see the angle of the shadow of the trees. And then they walk a block back to the planetarium and find a tree and use the protractor and get east and west that way. And some other team decides to come back at night and spot Polaris. So by the time we get done with something simple like the shadow, we've had about 5 different ways of figuring out what's east and what's west where I live. And that just really inspires me because they clearly are able to be creative and they kind of like it. And it's a lot more like science. So I'll stop there and love to have a discussion.
I'm going to reset the recording here.